You hear black hole and think one thing: darkness, inescapable gravity, the end of everything. But nature does not deal in simple endings. Black holes come in types, each with its own method of destruction. Some rip stars apart from a distance. Some spin so fast they warp the rules of physics. Some wander through space, orphaned and deadly. Others might be hiding in plain sight, remnants of the universe's first second. And one type, theoretically, exposes the singularity itself, naked and raw. No safety, no horizon, just the end of space and time, visible and waiting. Which ones exist? Which ones are real? What happens when you meet one? Before we dig into the brutal varieties, understand this: every black hole shares one trait. Once you cross the event horizon, the boundary where escape velocity equals light speed, you are gone. Not falling, not dying, gone. Time stops for the outside universe. For you, assuming you somehow remain conscious, you stretch. Spaghettification, physicists call it. Tidal force is so extreme that your head and your feet experience different gravitational pulls. Your body elongates atom by atom until molecular bonds snap. That applies to every single type we are about to discuss. If you value documented astrophysics and cosmology history like this, subscribe. It is the best way to support our work. Also, comment from which city you are hearing this from. Also, this script is researched and factual, using sources from NASA's Science Universe Black Holes documentation published October 2024, SOMS. The Physical Review D journal's January 2025 Black Hole Merger Analysis, and the European Gravitational Observatory's October 2025 Second Generation Black Hole Report. Institutions that represent the cutting edge of gravitational wave detection and black hole research. Now back to the information. The most common type is the stellar mass black hole. These form when massive stars die. Not just any star. A star needs at least 8 times the mass of our sun to even qualify. Most die as white dwarfs or neutron stars. But push past 20 to 25 solar masses, and the collapse cannot stop. The core implodes. Electrons and protons merge into neutrons. Then even neutron degeneracy pressure fails. What remains has 3 to 100 times the sun's mass, compressed into a sphere maybe 20 kilometers across. The smallest known stellar black hole sits at 3.3 solar masses with a diameter of 19.5 kilometers. That measurement comes from the binary system 2 mass J 05, 2 156, 58 plus 4 35 92 200, reported in June 2020. Stellar black holes do not sit alone. Most orbit companion stars in binary systems. The black hole strips matter from its partner through an accretion disk. As gas spirals inward, friction heats it to millions of degrees. That heat produces X-rays. That is how we find them. No light escapes the event horizon, but the stolen matter screams in X-rays before it vanishes. The Milky Way contains an estimated 100 million stellar mass black holes based on star formation rates and supernova frequencies. We have confirmed roughly 50 through X-ray binaries. The rest drift silent and invisible through interstellar space. 2025 brought a major confirmation. For decades, astronomers theorized that lone stellar black holes existed, black holes without companion stars, wandering solo, but proving it was nearly impossible. Black holes emit no light. Finding one alone meant catching it as it passed between us and a more distant star using gravitational lensing. In September 2025, Kailash Sahu at the Space Telescope Science Institute announced the first confirmed lone black hole in Sagittarius constellation. Hubble observations confirmed 7 solar masses moving independently. It is not the only rogue. It is just the only one we caught. Then there is the opposite extreme. Supermassive black holes. These anchor the centers of galaxies, not thousands of solar masses, millions, billions. Sagittarius, a star. The supermassive black hole at our Milky Way's center masses 4 million suns. That sounds enormous until you compare it to others. The black hole at the center of galaxy Holmberg 15, A, holds at least 40 billion solar masses. For context, our entire solar system out to Neptune spans roughly 60 astronomical units. The event horizon of a 40 billion solar mass black hole would span hundreds of billions of kilometers. How did they get so massive? No star explodes and leaves behind a billion solar mass remnant. The formation mechanism remains contested. One theory suggests they started as intermediate mass black holes and fed continuously on surrounding gas and stars over billions of years. Another proposes direct collapse. In the early universe, before the first stars formed, clouds of primordial hydrogen and helium could have collapsed directly into massive black holes without ever igniting fusion. These seed black holes would have masses between 100,000 and 1 million suns right from formation, giving them a head start on growth. Evidence for the direct collapse theory appeared in observations of quasars at extreme distances. These are supermassive black holes actively feeding. Their accretion disks so bright they outshine entire galaxies. Some quasars existed less than 1 billion years after the Big Bang. That is not enough time for a stellar mass black hole to eat its way to 1 billion solar masses. Not at observed accretion rates. Either the universe's first black holes formed big, or they fed far faster than current models predict. Research published in the Astrophysical Journal in 2023 and 2024 continues to investigate this puzzle using James Webb Space Telescope data showing these early monsters. Supermassive black holes do not just sit and feed passively. Many produce relativistic jets, streams of plasma ejected from near the poles at 99.9% light speed. These jets stretch for millions of light years. M87 Cas, the first black hole ever photographed by the Event Horizon Telescope in April of 2019, shoots a jet 5,000 light years long. The energy comes from the black hole's rotation and the twisted magnetic fields in the accretion disk. Matter does not fall straight in. It spirals. Magnetic field lines wrap around the rotation axis. Charged particles accelerate along these field lines and shoot outward. The physics is called the Blandford-Znajek process, described in 1977. Almost every large galaxy hosts a supermassive black hole. The correlation between black hole mass and galaxy bulge mass is tight. A galaxy with a bigger central bulge has a more massive black hole. This suggests coevolution. The black hole and the galaxy grew together, feeding back on each other. When the black hole feeds actively, it heats surrounding gas, blowing some of it out of the galaxy entirely. This quenches star formation. The black hole regulates how large its host galaxy grows. Without this feedback, galaxies would keep forming stars until they exhausted all available gas. Instead, supermassive black holes act as cosmic thermostats. Between stellar and supermassive lies the intermediate mass black hole. These range from 100 to hundreds of thousands of solar masses. For decades, they were theoretical. Stellar black holes form from collapsing stars. Supermassive black holes dominate galactic centers. But intermediate mass black holes had no clear formation path. They were too big to come from supernovae. They seemed too small to form from direct collapse, and observations found none. That changed with gravitational wave detections. On May 21, 2019, at 03:0229 UTC, the LIGO-Virgo collaboration detected a signal designated GBW190521. Two black holes, 65 and 85 solar masses, merged. The resulting black hole massed 142 solar masses. 8 solar masses radiated away as gravitational waves. This was the first confirmed intermediate mass black hole, announced in September 2020. It crossed the gap. It proved intermediate mass black holes exist, and that they form through mergers of smaller black holes. More candidates followed. In 2020, astronomers reported 3 XMMJ 215, 02 minus 0551, 08 in Aquarius, roughly 740 million light years away. In 2021, researchers found evidence for a 100,000 solar mass intermediate black hole in globular cluster B 023G78 in the Andromeda Galaxy. In 2023, analysis of globular cluster Messier 4 revealed an excess mass of roughly 800 solar masses at the center, potentially an intermediate black hole. A 2025 analysis identified 305 candidates by examining 1 million optical spectra from the Sloan Digital Sky Survey. X-ray emission confirmed 10 as legitimate intermediate mass black holes. Formation likely happens in dense environments. Globular clusters pack hundreds of thousands of stars into a sphere tens of light years across. Black holes sink to the center due to dynamical friction. There they collide and merge repeatedly. Each merger produces a larger black hole. Over billions of years, a stellar mass black hole grows through this runaway process into an intermediate mass black hole. Some may wander. Galaxy mergers displace black holes. A smaller galaxy merges with a larger one. The smaller galaxy's central black hole gets ejected or settles into orbit far from the new galactic core. These orphaned intermediate mass black holes drift through galactic halos, nearly undetectable unless they happen to disrupt a star. Which brings us to rogue black holes. Not a separate mass category, but a behavioral one. Any black hole, stellar or supermassive, can go rogue. It just means the black hole is not gravitationally bound to a galaxy center or a binary companion. It wanders, it drifts, it hunts. May 8, 2025, brought the first optical detection of a rogue supermassive black hole eating a star. Designated AT 2024 TVDE, the event occurred 600 million light-years away. A star drifted too close to a black hole positioned 2,600 light-years from its galaxy's core. The black hole tore the star apart in a tidal disruption event. The Zwicky Transient Facility in San Diego detected the flare. Hubble confirmed the location. This was extraordinary because tidal disruption events typically occur at galactic centers where supermassive black holes reside. Finding one offset confirmed that massive black holes wander far from home. Theories for how this happened include violent three-body interactions. If three supermassive black holes coexist in a galactic core after a merger, the chaotic dynamics of their orbits eventually eject one. Alternatively, the rogue came from a satellite galaxy that merged with the host long ago. The satellite's black hole never reached the center. It remains in orbit, or slowly migrates inward over billions of years. Either way, the black hole continues to feed. Radio observations with a very long baseline array showed a jet 7.2 light-years long and temperatures near 1 billion degrees Celsius. The black hole is active, growing, and far from where it should be. Then there is the dwarf galaxy Manga 12772-12704. In September 2025, astronomers announced a supermassive black hole sitting 3,260 light-years from the galaxy's core, feeding and producing a jet. Observations using the Manga survey and very long baseline array radio data confirmed intense activity between 1993 and 2023. This was not a brief flare. The black hole has been displaced for decades, possibly longer, and it keeps accreting matter. Lead scientist Han Tao from the Shanghai Astronomical Observatory suggested that as many as half of the massive black holes in dwarf galaxies may be displaced from their nuclei. Rogue stellar black holes exist in higher numbers but remain harder to find. Simulations suggest tens of thousands to millions roam the Milky Way. They formed in supernovae that gave them a natal kick, an asymmetric explosion that launched the newborn black hole at tens or hundreds of kilometers per second. Some reach thousands of kilometers per second if ejected during galaxy mergers. A black hole moving at 50 kilometers per second crosses the distance from Pluto to Earth in 20 years. Space is vast, so direct encounters with our solar system remain improbable. Estimates place the odds at 1 in a few hundred million over the next billion years, but they are out there, invisible and moving, only detectable if they pass in front of a star or disrupt nearby matter. Now we address the fourth theoretical type, primordial black holes. These did not form from stars, they formed in the first second after the Big Bang. In that instant, the universe was not uniform. Density fluctuations existed. Pockets of energy so dense they collapsed directly into black holes. No fusion, no supernova, just immediate gravitational collapse. These primordial black holes could have masses ranging from 100,000 times less than a paperclip up to 100,000 times more than the Sun's mass. Stephen Hawking proposed their existence in 1971. He calculated that any primordial black hole with mass below roughly 10 to the 12 kilograms would have completely evaporated by now due to Hawking radiation. Larger ones would still exist. The problem is, we have not found definitive proof. Searches using the Fermi Space Telescope launched in June 2008 look for terminal gamma-ray flashes from evaporating primordial black holes. As of 2024, none confirmed. That does not mean they do not exist. It means if they do, they are not evaporating in detectable numbers. One hypothesis suggests primordial black holes account for dark matter. Dark matter makes up roughly 85% of the universe's mass, but emits no light and interacts weakly with normal matter. Primordial black holes fit the profile. They emit no light. They interact only through gravity. If enough formed in the early universe with the right mass range, they could explain the missing mass. However, constraints from gravitational lensing surveys and cosmic microwave background observations limit how much dark matter can consist of primordial black holes. Current estimates suggest they make up only a small fraction, if any. The quantum memory burden effect adds a twist. Research published in Physical Review D in January 2025 described how evaporating black holes might stabilize after losing half their initial mass. Hawking radiation predicts black holes radiate energy and shrink. The smaller they get, the hotter they become, accelerating evaporation. But quantum effects suggest the information stored inside the black hole, encoded in quantum states, becomes energetically favorable to retain rather than radiate. The black hole stops evaporating. If true, this opens a new mass window. Primordial black holes with masses below 10 to the 10 grams, previously thought to have evaporated, could still exist as stable remnants. These remnants might constitute dark matter. Gravitational waves could confirm or disprove this. Primordial black hole formation in the early universe would produce gravitational wave signals. Future detectors like the Laser Interferometer Space Antenna, or LISA, scheduled to launch in 2035, will search for these signals. If primordial black holes exist in significant numbers, LISA should detect their formation signatures or their mergers with other compact objects. Then we address rotating black holes, technically not a separate type, but a property any black hole can have. However, rotation fundamentally changes the physics. A non-rotating black hole follows the Schwarzschild metric tau, discovered by Carl Schwarzschild in 1915. It has a spherical event horizon and a point singularity at the center. A rotating black hole follows the Kerr metric, discovered by Roy Kerr in 1963. The event horizon is oblate, flattened at the poles. The singularity is not a point, but a ring. Rotation creates an ergosphere, a region outside the event horizon where space-time itself is dragged around the black hole. Inside the ergosphere, nothing can remain stationary. Everything must rotate with the black hole, even light. This frame dragging, also called the lens-Thirring effect, was predicted by general relativity and confirmed through observations of black holes and neutron stars. The Penrose process exploits the ergosphere. A particle enters the ergosphere and splits. One fragment falls into the black hole with negative energy. The other escapes with more energy than the original particle. This extracts rotational energy from the black hole, slowing its spin. Black holes spin fast. GRS 1915 plus 1. O5 in the Milky Way rotates 1,150 times per second, approaching the theoretical limit. The spin parameter, a dimensionless number between 0 and 1 das, measures rotation. 0 is non-rotating. 1 is maximum spin, GRS 1915 nears 1. M87's supermassive black hole has a spin parameter around 0.9. Sagittarius, a star, sits at 0.1, relatively slow. On January 14, 2025, LIGO detected GW2 50114, or the clearest gravitational wave signal ever recorded. Signal-to-noise ratio reached 77 to 80, far exceeding the previous record of 42. The merger involved two black holes, 33.6 and 32.2 solar masses, both rotating. The merged black hole massed 62.7 solar masses. 3.1 solar masses radiated as gravitational waves. The clarity allowed researchers to identify the first overtone of the Kerr solution, confirming predictions about how rotating black holes ring after mergers. This also verified Hawking's area theorem, which states the total surface area of merging black holes must increase or remain constant. It did. Two detections in late 2024, GW241011 and GW241110, showcased second-generation black holes. These are black holes formed from previous mergers. GW241011 occurred October 11th, 2024, 700 million light-years away. A 17 solar mass black hole merged with a 7 solar mass black hole. The 17 solar mass black hole spun rapidly, one of the fastest ever detected. GW241110 occurred November 10th, 2024, 2.4 billion light-years away. A 16 solar mass black hole merged with an 8 solar mass black hole. The larger black hole spun opposite its orbit, a first. Both events suggest hierarchical mergers in dense environments like globular clusters or galactic nuclei, where black holes merge repeatedly, growing larger and spinning faster each time. Published in the Astrophysical Journal, Letters in October 2025, the findings confirm that black holes do not just form once. They collide, merge, and create new black holes that go on to merge again. July 2824 brought GW23112 the most massive binary black hole merger detected to date. The black holes massed in a range most models say should not exist. Supernovae do not produce black holes this large. Pair instability supernovae, which occur in stars between 130 and 250 solar masses, blow the star apart completely, leaving no remnant. Yet GW23112's components exceeded typical supernova black hole masses. Both spun close to the theoretical limit. The merged black hole may have formed through successive mergers in a dense cluster or active galactic nucleus. Researchers Margaret Milhouse and Surabhi Sachdev from Georgia Tech highlighted that this challenges stellar collapse models and suggests black holes grow through chains of mergers rather than single formation events. The fastest spinning black holes create interesting problems. At spin parameter 1, the event horizon shrinks to half the Schwarzschild radius, push spin higher, and the event horizon disappears. What remains is a naked singularity. Cosmic censorship, a conjecture by Roger Penrose, states naked singularities cannot exist. Nature always hides singularities behind event horizons, but the math allows them. Rotate or charge a black hole past extremal, where mass equals charge or spin reaches maximum hoing, and the horizon vanishes. In February 2024, Christoph Keeley and Ryan Unger published a proof in Physical Review Letters showing that extremal black holes can form. They constructed smooth solutions to the Einstein-Maxwell-Vlasov equations, showing that charged matter, under precise conditions, collapses to form extremal Reissner-Nordstrom black holes. These have maximum charge for their mass. Add more charge, and rather than forming a naked singularity, the matter disperses. No collapse occurs. The proof contradicted the third law of black hole thermodynamics, which stated extremal black holes cannot form in finite time. Kalo and Unger showed they can. They sit on a critical threshold. This resolved a 50-year debate. However, July 2025 brought a new twist. Research on dilatonic black holes, theoretical objects with a scalar field, showed that extreme versions expose their singularities in finite time through Hawking radiation and the Schwinger effect. The Schwinger effect spontaneously creates particle-antiparticle pairs and strong gravitational fields. For dilatonic black holes above solar masses, pair production stops at extremality. Hawking radiation continues, eroding the event horizon. The singularity becomes naked. This challenges cosmic censorship. If confirmed, it means some singularities do become visible, at least for specific black hole types predicted by string theory and quantum gravity, Standard Schwarzschild and Kerr. Black holes probably do not produce naked singularities. Attempts to overspin or overcharge them have failed. Werner Israel's 1986 proof and subsequent work by Mihalis Daframos and others showed that you cannot overcharge a black hole by dropping charged matter into it. The work done adding charge increases the mass proportionally. The event horizon grows. You never cross the extremal threshold. Similarly, spinning up a black hole by feeding it, rotating matter does not exceed the spin limit. Cosmic censorship holds for realistic scenarios involving ordinary matter. Micro-black holes occupy a different regime. These would have masses far smaller than stellar black holes, possibly down to the Planck mass, roughly 10 to the negative 8 kilograms. At that scale, quantum effects dominate. Hawking predicted in 1975 that micro-black holes evaporate almost instantaneously. A black hole's temperature is inversely proportional to its mass. Smaller black holes are hotter. A Planck mass black hole radiates at 5.6 times 10 to the 30 Kelvin. The emitted particles carry energy comparable to the black hole's mass. Evaporation accelerates. The black hole explodes in a burst of gamma rays. The Large Hadron Collider at CERN was tested for micro-black hole production. Some theories involving extra spatial dimensions predict black holes could form at tera-electron-volt energy scales accessible to particle accelerators. If they formed, they would evaporate instantly. No danger exists. Cosmic rays strike Earth's atmosphere with far higher energies, reaching hundreds of tera-electron volts. If collisions at those energies produced stable micro-black holes, Earth would have been consumed long ago. It was not. Micro-black holes either do not form at accessible energies, or they evaporate too quickly to matter. In 2024, researchers at the University of Amsterdam demonstrated analog Hawking radiation using superconducting qubits. They built a chain of 10 transmon qubits with tunable couplers, creating a simulated curved space-time. Particles in the system behaved as if near a black hole event horizon. The experiment confirmed stimulated Hawking radiation, verifying theoretical predictions. The results, published in Nature Communications, showed entanglement dynamics matched Hawking's predictions. While not a real black hole, the analog system validated the quantum mechanics underlying black hole evaporation. The final, most speculative type, the naked singularity, not technically a black hole because it has no event horizon. Instead, the singularity sits exposed. General relativity allows their existence mathematically. Rotate or charge a black hole past the extremal limit, and the math says the horizon disappears. What you see is the singularity. A pointer ring where space-time curvature becomes infinite. Naked singularities break physics. At a singularity, general relativity fails, density becomes infinite, curvature becomes infinite. The equations produce nonsense. If we could observe a naked singularity, we could not predict what happens. Causality breaks down. Cosmic censorship exists to prevent this. Roger Penrose argued in the 1960s that nature forbids naked singularities. All singularities must hide behind event horizons. But cosmic censorship is a conjecture, not a proven law. Counterexamples exist in specific solutions to Einstein's equations. Some involve fine-tuned initial conditions, unlikely to occur naturally. Others, like the dilatonic black hole case mentioned earlier, suggest naked singularities might form under realistic quantum processes. Research published in Physical Review Letters in November of 2024 by physicists at Durham University showed that quantum effects, specifically semi-classical corrections, tend to prevent naked singularities by modifying the event horizon structure. Quantum-dressed singularities emerge, where quantum mechanics blurs the singularity enough to preserve a form of censorship. Testing this requires observing a naked singularity or proving they cannot exist. Distinguishing a naked singularity from a black hole is difficult but possible. The lens-Thirring precession, the rate at which a gyroscope precesses near a massive rotating object, differs between black holes and naked singularities. A June 2025 paper in Simple Science described how the precession frequency depends on spin and surface gravity. Naked singularities lack event horizons and therefore lack surface gravity in the same sense. Their precession patterns differ measurably. If we find an object with the right precession signature, we might have found a naked singularity. None confirmed yet. Every observed candidate so far fits black hole models. But the search continues. Projects like the Event Horizon Telescope, which imaged M87 and Sagittarius A star, provide high-resolution observations of regions near event horizons. If naked singularities exist, future observations might catch one. Across all types, black holes share the no-hair theorem. A black hole is completely described by three properties: mass, charge, and angular momentum. Nothing else. No matter what fell in, whether stars or planets or antimatter or dark matter, the final black hole depends only on those three numbers. All other information is lost, creating the black hole information paradox. Quantum mechanics says information cannot be destroyed. General relativity says anything that falls into a black hole is lost forever. Stephen Hawking proposed in the 1970s that black holes evaporate via quantum radiation. But that radiation appears random. Where did the information go? Solutions proposed include quantum hair, subtle quantum corrections that encode information in Hawking radiation, remnants, stable Planck mass, black holes that store information, holography, where information is encoded on the event horizon surface, and modifications to general relativity or quantum mechanics. None are proven. The paradox remains open. The universe contains billions of black holes. LIGO, Virgo, and KEGRA have detected hundreds of mergers. Each detection refines our understanding. Each merger confirms general relativity in extreme conditions. The fourth observing run, 04 began in May 2023 and continues through 2025. Upgrades improve sensitivity. More detections come weekly. The catalog grows. Future detectors expand reach. LEGO India is planned. The Einstein telescope, a proposed underground detector in Europe, would increase sensitivity tenfold. LISA, launching 2035 as Darzus, detects lower frequency gravitational waves from supermassive black hole mergers, an extreme mass ratio in spirals where stellar black holes spiral into supermassive ones. The Vera Rubin Observatory in Chile will survey the sky, detecting transient events like tidal disruptions from rogue black holes. Each instrument adds a piece. Every type of black hole tells a story. Stellar mass black holes trace star formation and supernovae across cosmic history. Supermassive black holes reveal galaxy evolution and the role of feedback in shaping large-scale structure. Intermediate mass black holes bridge the gap, showing how smaller objects grow into giants through mergers. Rogue black holes expose the violence of galaxy interactions and three-body dynamics. Primordial black holes probe the universe's first moments and might solve the dark matter mystery. Rotating black holes test general relativity's predictions about frame dragging and gravitational waves. Extremal and naked singularities push the boundaries of what physics allows. The latest mass grave from gravitational wave astronomy sits in the data. On January 14, 2025, LIGO recorded GW250114. The signal-to-noise ratio of 77 to 80 confirmed not just the merger, but the ring down, the phase where the merged black hole settles into its final shape. It rang like a bell, oscillating at frequencies predicted by the Kerr metric. The overtones matched. Hawking's area theorem held. The black hole's surface area increased as predicted. This was not just another detection. This was confirmation at unprecedented precision. In the months and years ahead, more discoveries will come. The fourth observing run continues. Detectors improve, theories refine. Black holes do not reveal themselves easily. They hide. They wander. They evaporate. They merge. But every observation chips away at the darkness. Every signal carries information encoded in the ripples of space-time itself. Every detection moves us closer to understanding the universe's most extreme objects. We started with darkness and gravity. We end with light from the past. Not optical light, but gravitational light. The warping of space-time that carries energy across 1 billion light years and arrives, faint but detectable, at instruments on Earth. Those ripples tell the story of black holes colliding, of matter crushed beyond comprehension, of singularities hidden or exposed, of rotation so fast it drags space-time around, of orphans drifting through galactic voids. The universe makes black holes in every mass range we can detect, 3 solar masses to 40 billion. It makes them alone and in pairs. It makes them in the first second of time and in the collapse of stars today. It spins them to the edge of physics. It hides their singularities behind horizons or possibly exposes them. It wanders them through space, displaced and feeding. It chains their mergers, building second and third generation giants, every brutal type of black hole explained, not with speculation but with observations, with gravitational wave detections cataloged in peer-reviewed journals, with X-ray binary measurements, with Hubble images of tidal disruptions, with LIGO signal-to-noise ratios published in Physical Review D and the Astrophysical Journal Letters, with theoretical proofs from researchers at MIT and Cambridge and Durham and Shanghai, with data from instruments built across decades by thousands of scientists who pointed their detectors at the sky and waited for the universe to speak in gravity. The universe spoke. We listened. The story is not gentle.